Hey guys, welcome back to my channel. I'm Arvind from PrecisionDataScience. Today we're going to be working on Kaggle's second playground series, that is Multiclass Obesity Risk Prediction. In case you aren't subscribed to the channel, please consider subscribing and like the videos if you find it useful. So without further ado, let's dive into the video. First, we'll be importing warnings to have a cleaner output, and then NumPy and Pandas to work on the array data and data frame. Next, we have Matplotlib and Seaborn for data visualizations. We will read the two CSV files, rain and test file, using read_CSV method and assign it to a data frame, df and df_test. Since IDs are unique to each customers and may not play a role in deciding whether a customer is obese or not, we can drop these columns with the drop method. Before that, we're going to assign the ID values from the test data to a new variable test_ID so that it can be used to make predictions on the test IDs. We will display the first few rows for each dataset using head method, and here we can see the columns data such as gender, age, height, weight, CH2O, smoke, employment, etc. for both train and test data. One thing that distinguishes the train data and the test data is presence of NoBeSdat column in the train data, which shows the status of obesity level in the customers. For the test data, we need to create predictions for the NoBeSdat column and submit to the Kaggle computations for results. df_info method provides a summary of data frame which includes missing values and the data types for each column. Here we have 20,758 entries for the training data and 13,840 entries for the test data with all non-null values, which means that there is no missing data. With any unique method, we can see the number of unique values in each columns, and generally columns with categorical data will have less unique values. We will assign the categorical columns to a new variable categorical_columns by selecting the object data type from both train and test dataset. We're going to check the unique values in the obesity column with unique method, and here we have 7 unique categories. Next, we will create a dictionary to assign the numerical values to each category with hierarchy ranging from insufficient weight being low to obesity type 3 being high, and we'll replace the categorical values with corresponding numerical values. You can also try using other encoding techniques such as label encoding, one-hot encoding, etc. After replacing the target column in the train dataset, we'll move on to other columns. Applying unique method to entrance column shows the different means of transportation used by the individuals. We have 5 unique values, and we can replace the categorical data with 5 ordinal values ranging from bike being a low value to public transportation being high value. After replacing the categorical data for both train data and test data, we're going to check the unique values for the CAC column and CALC column, which shows the frequency of food consumption between meals and frequency of alcohol consumption respectively. We're going to create a dictionary for both the columns with no being a low value to always being high value, and we'll replace the categorical values with corresponding numerical values. Next, we have categorical columns such as gender, smoke, etc. with either yes or no values, and for that we're going to apply the one-hot encoding technique to create one column per each category. Pandas has a simple method called getDummies, which applies the one-hot encoding technique to the categorical columns. We're going to apply the getDummies method and check the columns after one-hot encoding. Since one column is enough to represent 2 values, we can drop one column for each category with the drop method. After dropping, we can check the columns available in the dataset. With info method, we can see that all the categorical columns data has been converted to numerical values. We're going to create a new column, BMI square root, by dividing the square root of weight column with the height column. Next, we'll convert the data type to float and plot the correlation heat map with index sorted in ascending order. The correlation values have been annotated. Here we see negatively correlated features like consumption of food between meals, that is CAC, physical activity frequency, that is FAF, etc. And we have positively correlated features like BMI square root, weight, family history with overweight, etc. In order to make predictions, we have to separate the features and the target column of the trained dataset. For features, we are considering all the columns except the target column, that is NoBeSdat column, and for the target column, we are considering only the NoBeSdat column. For training the machine learning model, we need to split the data into training and validation set. For that, we'll import train test split from the scikit-learn library. We will consider 20% for the validation set and 80% for the training set with a random state to maintain consistency. Moving on to machine learning model implementation, here we have XGBoost Classifier, which uses gradient boosting method, that is combining weak learners with a learning rate and regularization, enabling them to evolve into a strong model. We'll instantiate the model with a random state 3361 and fit the model for the training data. After the model learns by fitting the data, we're going to predict the label values for the validation set. For evaluation, we're going to import certain metrics such as accuracy score, classification report, and confusion metrics. Here we have overall accuracy of 90.41% and F1 score varying from 79% for the class 2 to 100% for the class 6. F1 score is basically the harmonic mean of precision and recall. Next, we'll plot the confusion matrix, which shows the correct predictions along the diagonal and wrongly predicted values as either false positive below the diagonal or false negative above the diagonal. To verify the values, we will do a cross-validation across the dataset using cross-val score from the scikit-learn library. We will apply the cross-validation across the training dataset with a CV value of 5 folds. After displaying the scores, we can see that the mean value is 90.05% and values range with a standard deviation of 0.31%. Now, in order to make improvements to the machine learning model, we'll try to optimize the parameters within the XGBoost. We have used RandomizedSearchCV method for the hyperparameter optimization and we'll try to instantiate the model with the optimized parameters. In case if you want to see how RandomizedSearchCV works, please check out my previous video on background prediction. After predicting the accuracy on the validation set, the accuracy score turns out to be 91.21% with a mean value for the 5-fold cross-validation as 90.68%, which is an improvement from the base model. In order to make predictions for the test data, we'll import joblib library and save the XGB model with the dump method. Next, we'll load the model and make predictions for the test data df_test. We will combine the predictions with the test IDs and convert the predicted values into categorical data as required with the Kaggle computation using this dictionary. After saving the CSV file using to_CSV method, we'll upload the file to the Kaggle website and check the prediction accuracy. The prediction accuracy is 90.54% and final rank is 1304 out of 3746 competitors. So we have achieved top 35%, which is a small improvement from the previous playground series. So that's all I have today, guys. If you enjoyed this video so far, please like the video, share, subscribe and hit the bell icon to see more content. Thank you.